Hi, so I'll talk about this paper called Light Field Reconstruction using Sparsity in the Continuous Fourier domain. Initially, I'll just set up the problem and talk about how they solved it, and eventually, I'll get to my reimplementation and some observations I made while reimplementing it. So the problem that we are trying to solve is this: we only have access to a sparse set of views of a light field that are defined by a set of lines in the angular domain, and we wish to reconstruct the entire light field from the sparse set of views. If you look at the 4D light field spectrum and take an angular slice of it, you'll observe that only a sparse set of angular frequencies have non-zero coefficients, and this is the prio that you use to reconstruct the entire light field from just a sparse set of views. The problem now boils down to just estimating the positions of the sparse angular frequencies and their corresponding coefficients. And the first thing to note in order to do this is that we already have access to 1D projections of the 2D angular spectrum. And I'll show you what I mean by that in the next few slides. So, say this is the sampling pattern that we have with six different lines. And the first thing you do is to compute a 2D Fourier transform for each of these views along the spatial dimensions. And then you compute a 1D Fourier transform for every spatial frequency along each of these lines. And according to the projection slice theorem, those 1D Fourier transforms are the projections of your 2D angular spectrum, and you can use a voting scheme very similar to the Huff transform to recover the positions of the sparse angular frequencies. And this is just an example. This is just an example where you have three different non-zero coefficients in the 2D spectrum, and if you project it along three lines and then use those projections to vote back into the 2D grid, you can quite easily recover the original sparse angular frequencies. And this is from my own re-implementation of the same thing. On the left is the actual 2D angular spectrum, and on the right is the uh, estimated frequency positions from using my re-implementation. This is just another example of the same thing. And another thing that I did not talk about and the paper doesn't talk about much either is the thresholding scheme that decides whether a projection votes for a line or not. And the paper suggests that you should just use a threshold, the lowest possible threshold that still keeps the system of linear equations that you use to solve for the coefficients overdetermined. But what I noticed is that that does not work very well. And on the left is a reconstructed view inside the sampling region, and that looks great. But on the right is a reconstructed view outside the sampling region, and that's just noise. So it's not very useful. But what I noticed is that with a much higher threshold, it generalizes much better to views outside the sampling region, with only a marginal drop in quality for views inside the sampling region. Another thing the paper talks about is the effect of windowing effect. Is the windowing effect, uh, and that manifests itself as the sparsity being ruined in the discrete domain when you go from the continuous domain to the discrete domain. And that's because you sample only a finite window of the light field, and that corresponds to convolving with a sinc function in the Fourier domain. And if you convolve a sparse signal with a sinc function, that signal is not sparse anymore. So the way they deal with that is by optimizing for sparsity in the continuous domain, and the way they do that is by using the voting scheme as an initialization and optimize and like fine tuning the positions of the angular frequencies using gradient descent. And yeah, this is basically what they do. They have the positions of the sparse frequencies on a discrete grid, and they use gradient descent to fine tune them. I implemented this and I did not find a significant improvement. Uh, but yeah, so one of the things that the paper claimed that would improve after the fine tuning step is are these ghosting artifacts for the peripheral views, and that's because you would essentially smooth over a neighborhood of views, and that's more pronounced in the peripheral views because it wraps around to opposite ends of the primary domain. But I did not really notice an improvement in this. Yeah, so thank you.